In this video, I'll focus on angular impulse. Previously, we learned that angular momentum is product of moment of inertia times angular velocity. Now, angular impulse. Angular impulse is actually rate of change of L, delta L over delta T. So let's start from the beginning. I know in linear motion, force is written as delta P over delta T, rate of change of momentum. So delta P is going to be force times delta T. Delta P is called change in momentum, or let's say impulse. Here in rotational motion, we have almost the same thing. Torque is written as delta L over delta T. Torque is rate of change of angular momentum. Now delta L is going to be torque times delta T. Torque times the time interval. Delta L is change of angular momentum, or let's say angular impulse. According to this equation and regarding the integration rules, if I draw the force time graph, the area under the graph, regardless of the shape of the graph, is changing momentum or the impulse. Here we have almost the same thing. If I draw torque time graph, the area under the torque time graph is going to be change in angular momentum or angular impulse. Look at this question. A flywheel of the moment of inertia 0.07 kilogram meter square is driven by an electric motor that provides a torque that varies with time t. This is the torque time graph. Everything is in SI. The graph shows the variation with time t of the net torque applied to the flywheel. The flywheel is initially at rest. Calculate part A, the angular impulse on the flywheel until t equals 5. I have the torque time graph, and for finding the angular impulse change in angular momentum, I just need finding the total area under the graph from 0 to 5. Here we have a trapezoid. Large base of this trapezoid is 5, small base is 1, and the height is 5. So delta L is large base plus small base times height divided by 2. This is 3 times 5, 15. So it's 15 Newton meter second, the SI unit of delta L. Part B. The angular speed of the flywheel when t is equal to 10. I should cover the whole graph. Angular speed of the flywheel is actually the final omega. Final omega, but you just remember the initial omega was 0. It starts from rest. So if I find delta omega, it's actually omega final, because omega initial is 0. Omega final minus 0 is again omega final. So if I find delta omega, I have found omega final. That's the goal of the question. How to find that? You remember delta L was I times delta omega. Okay? Here I have the I. It's given in the question, 0.07. So if I know the I, 0.07, and if I know the total change in angular momentum, that's the angular impulse, the total area under the graph, I can easily find the delta omega, and that's actually omega final. And it's my goal of question. So let's start from the scratch. Delta L, the total area under the graph. The large base of this trapezoid is 10. Small base is from 4 to 9. So this is 5. This is 5 plus 10 times the height. Height of that is again 5 divided by 2. This is delta L. Right side I have 0.07. This is the I given in the question. And delta omega is actually the final omega. Regarding the omega initial, that's 0. So we can easily find the answer. The omega is going to be 500 radians per second. This is the final omega after 10 seconds. Part C of the question. The average angular acceleration of the flywheel during the first 10 seconds. Average angular acceleration. Angular acceleration is delta omega over delta t. The whole motion takes 10 seconds. So it's 10. But delta omega is omega final minus omega initial. Omega initial is 0. Starts from rest. So I should just divide omega final by 10. And omega final is actually 500. We found it already. So the answer is 50 radian per second squared. Another question. Two rocket thrusters T1 and T2 separated by a distance of 80 meter are used to rotate a space station around its axis. Here I have a thruster T1 and the other thruster T2. Each are providing 1 kilonewton of force tangentially acting on that disk as the model of that space station, and they are separated by the diameter of this large construction. Let's say this is 80 meter as given in the question. Each of the thrusters provide a 1 kilonewton force at right angle tangential actually to the line joining the thrusters. Okay, the moment of inertia of the space station about the point halfway between the thrusters is 2.8 10 to 8. It's exactly rotating around the center. The space station rotates initially in a clockwise direction. Okay, it's a clockwise direction at the beginning of the consideration of this change with the period of 20 minutes. So period is actually in SI unit is 20 times 60 in seconds. Thrusters operate for 30 seconds. Okay, let's go to the first part. Calculate the initial angular momentum of the space station. Okay, initial angular momentum is actually L at the beginning. I know omega initial, look at the question, omega initial is 2 pi divided by t, the period at the beginning. Okay, so t just is given in minutes, is just converted to second, and we are done. We can easily find the L as I omega. Omega is 2 pi divided by the period in second. I is given in the question 2.8 10 to 8. Done. L is 1.47 10 to 6 Newton meter second. This is the initial angular momentum. Okay, before any change. Just keep in mind that here the thrusters will act on the system, will work for 30 seconds given the question. Part B, the angular impulse delivered to the space station by the thrusters. Okay, thrusters, as I mentioned, will work for 30 seconds. Here, I know that thrusters are working in opposite directions and they have equal forces separated by a distance of 80. So it seems to be like a couple of force. I have F and I have negative F like a couple separated by a distance of 80. So the torque due to this couple is supposed to be F, one of the forces, times the separation, 80. Okay, why should we need the torque? Because torque times the time interval of action of the forces is change in angular momentum or the angular impulse. That's it. This is why we need the torque. So torque is going to be the one of the forces, 1 times 10 to 3 because it's 1 kilonewton. In SI, it's 1 times 10 to 3. 80 is the separation of the forces, and 30 is the time interval given. Okay, this is the change in angular momentum or the angular impulse, 2.4 10 to 6 Newton meter second. Part C, the final rotational period of the space station. The space station was in clockwise rotation initially, and then these forces will accelerate it and make it rotating faster. Okay, we have the change of angular momentum, so we can find the final rotational period of that like this. Delta L, as L is I omega, so L minus initial L is I times omega minus omega initial. It's exactly what you see. So I times change in omega is change in angular momentum. We have already found the change in angular momentum. We can use it here. I also is given in the question, and then initial omega was supposed to be 2 pi divided by the initial period, and then omega will be this initial omega, and the omega will be 2 pi divided by final period, and then we can find it. Just there is a small trick I have used. Here I have delta L, We have no problem with that. This is I given in the question, 2 pi divided by t, 2 pi divided by t. Here, 1 over t and 1 over initial t. Why should I convert this to second? We can find it in minutes. So this is exceptionally could be written in minutes, not necessarily in SI units. So let's use it in 20 minutes. And then we will find the final period of the system again in minutes. Of course, you can use second, but just to make it simpler, I did it like that. So the final period of the system that seems to be in faster rotation is 7.6 minutes. Why faster rotation? Because the period is less than 20. So less period means larger frequency. So it's supposed to be rotating faster than the initial omega it had. The reason is that these thrusters are accelerating to the same direction as it was rotating. That's all. Thank you for your attention. I hope you learned what the angular impulse is. Take care. See you soon.